it is, so, I mean, what we want is we want it to be less than halfway. So in other words, the distance between any pair, so this is the minimum distance between any pair of code words. And we can correct up to less than halfway. So let's remember that this is, so in other words, it seems like d-min over 2, something less than d-min over 2. So basically what I want is the smallest integer, or the largest integer, less than d-min over 2. And I will spare you the futzing around to try to get that. In fact, the largest integer less than d-min over 2 is given by the following. Does everybody know what the floor symbol means?
Yeah.
Floor, 1/2 d-min minus 1. But effectively what that means is the largest integer less than d-min over 2. And it must be strictly less than. Not less than or equal to. It must be strictly less than d-min over 2. Okay, so let's go back to d-min equals 2. Firstly, let's think of this. What's the largest integer less than d-min over 2? So d-min is 2, 2 over 2 is 1. What's the largest integer less than 1? 0. So therefore I can correct 0 errors if d-min is 2. D-min is 3. Okay, first off, 3 over 2 is 1.5. What's the largest integer less than 1.5? 1. So therefore, and if I plug that in here, 3 minus 1 is 2. 2 over 2 is 1. Floor over 1 is 1. So therefore, minimum distance of 2, I can correct 0 errors. Minimum distance of 3, I'm guaranteed to be able to correct at least 1 error.
And this is with no error correction code. This is just having sequences.
So this is the error correcting code. So in other words, if I give you a bunch of, basically what is a code? It's,
well, I mean, with no redundancy bits.
Oh, I see what you're saying.
Code words, correct.
So that's a good question. So what is a code? Basically a code is just a set of sequences. So I guess that's worth mentioning. So how do I encode? If I give you, basically, if I give you a bunch of sequences, a set of sequences, and I say this is a code and it has d-min of 3. I mean, this is the code. So what you could do is you can just find some way of assigning, for instance, in this case, you can assign 0 to 0, 0, 0, and 1 to 1, 1, 1. In other words, information bits of 0 to 1. And away you go. So in other words, instead of 0, you send 0, 0, 0. Instead of 1, you send 1, 1, 1. Down here, same thing. This could be 0. There's 4 of them, so there's 2 input bits and 3 output bits, if you like. So it would be 0, 0, 0, 1, 1, 0, 1, 1. So abstractly, that's how a code works. It's just you assign input sequences to output sequences. So in the single parity check code, it turns out that there's an algebraic relationship between these 2 bits and that one. But that doesn't necessarily have to happen. All that you require of a code is just that it's a list of sequences. Now, the next thing we're going to talk about actually is called linear block codes, which is how can you, instead of being given a list of sequences, how can you dynamically construct sequences with a certain Hamming weight, or with a certain minimum Hamming distance. And to do that, we use parity checks. We use like more and extended parity checks.
So, sir, the rules that we concluded, this is only specific to single parity bit checking, or for some other schemes it's different?
No. So if I give you a code, remember, a code is just a set of sequences. And so on. So a whole bunch of sequences. That's a code. So in other words, you can assign, let's say there are, let's say the cardinality of the code is 2 to the k. Then you have k input bits, and every code word has, so I've defined the length of my code as n. So I take k input bits and I produce n output bits. How you do this is up to you. So you could, for example, form a huge lookup table and take every k input bits and assign it to some n output bit sequence from the code. What we're about to talk about is linear block codes, which is simply a method. Basically, it's a method of constructing n output bits from k input bits that have a certain structure. So that's much more efficient. So storing 2 to the k for any non-trivial k is not a very efficient way to operate a code. Basically, you have to store and sort and search, and that's not how we like to operate. But a linear block code, basically, what you can do is you can take k input bits and do a linear transformation and produce n output bits, basically with matrix multiplication.
Can you compress data and if you compress data and send it, it's not always gonna, you can't always do that.
What you can do is you can compress first and then encode, and then apply an error control code on top of the compressed data. So when you're compressing data, all you're doing is transforming certain bits into other bits. So the error control code doesn't care what the input bits are, whether they're compressed or not. All the error control code cares about is what bits you want to protect with its code. So basically, compression, what's going on here? N is usually greater than k. In fact, in every example we've had so far, the number of output bits is greater than the number of input bits. And that's obvious. If that was not true, then there would be no redundancy. So compression basically takes, let's say, n prime, and produces n prime bits and turns it into k bits, where k is less than n prime. So that's compression. And then I can take those k bits and encode them as an error correcting code with extra bits. So in other words, generally the procedure is first we compress and then we expand. The problem is this redundancy can be exploited by a decoder, but it's not properly structured. So we can't generally make guarantees about things like Hamming distance. But what we do first is we compress, so we squeeze out all of the redundancy that is not useful to us, and then we add extra redundancy that we can carefully control in order to correct errors on the channel. There's actually a theorem to this effect that there's no loss if by doing these steps separately. Okay, so in the remaining time that we have, let's talk about linear block code.